Welcome everybody, welcome Calista. I'd like to introduce Calista Bernard from Stanford University, talking today about twisted Dyer-Lashof operation.
Great. Yeah, thanks so much for the invitation, and thanks everyone for coming to the virtual seminar. So please let me know if I start writing too small or if I accidentally move the paper away or if you can't see or whatever. So today I want to tell you about Dyer-Lashof operations on homology with twisted coefficients. So in case you're not familiar with Dyer-Lashof operations more classically, let me start out by talking about the classical case. So Dyer-Lashof operations are defined on the homology of EN algebras. And sort of one piece of intuition you can keep in mind here is that if we look at the homology of a free EN algebra, so here this notation means free EN algebra on X. And here, for this talk, I'm going to mostly be talking about chain complexes, but you can have X be a space or a spectrum or whatever you like. So if I care about this homology of a free EN algebra on X, this should be free on the homology of X in some sense. We have to make sense of what exactly that means, but there's a monomorphism from this homology to this homology, and so we'd like for this to be free on the homology of X in some sense. And it turns out that operations on the homology are the right way to make sense of this. So first, I should finish writing this first. So I'll start by saying something about how we actually define operations, and then I'll come back to this statement about freeness. So if we have X, an EN algebra in chain complexes, so here I'll always work with chain complexes over some field F. So if X is an EN algebra in chain complexes, and I care about the kth homology of X, let me pick some class little x in the kth homology, these are in bijection with homotopy classes of maps from a certain chain complex to X. So here these are homotopy classes of maps. And this chain complex here is a copy of F, in grading K and zeros everywhere else. So homology classes are in bijection with homotopy classes of such maps, and given one of these maps, from this copy of F in degree K to X, we can apply the free EN algebra functor to obtain a map from the free EN algebra on this copy of F in degree K to the free EN algebra on X. And since X is an EN algebra, we have a multiplication map to X. So let me call this composition F lower X. So now given this composition, we can pass to homology. And so for any homology class, call it gamma, in the mth homology of, the free EN algebra on this copy of F in degree K, we get a homology operation. And the way that that works is this operation goes from the kth homology of X to the mth homology of X. And we take this class little x, and we take its image under the induced map from fx applied to gamma. So this is an example of a unary operation. It takes one input. And in general, we get J-area operations, so operations with J inputs, going from HK1 of X cross, and here I actually do mean Cartesian product. We're not going to require that our operations pass through tensor products. Many of them will, but not all of them. And my operations landing in HM of X, such operations come from the mth homology of the free EN algebra on a direct sum of these chain complexes that are a copy of F in an appropriate degree. So this is a sort of very hands-on approach, but the more formal way to state what I've just said would be to view homology as a functor from the homotopy category of EN algebras and chain complexes to sets. And an homology operation would be a natural transformation of these functors. And then some version of the Yoneda lemma will give us this result that operations come from this homology on a free EN algebra. But if you say it that way, you have to be a little bit careful about model structures. And so I decided to say it this way instead. But we can actually rewrite this a little bit to be a bit more specific about where operations are coming from. So I'll just make a quick little aside. If you'll recall that for any x, the free EN algebra on x has the following model. I take the direct sum over L greater than or equal to 0 of chains on the little n disks operad. So this is the little n disks operad in Lth arity. And I tensor this over the Lth symmetric group with x tensored with itself L times. So that's a formula for the free EN algebra on x. So in particular, if we apply this splitting up here, we get that this homology splits as a direct sum indexed by L of mth homology of chains on the little n disks operad. And I sort of ran out of space, so I won't finish it. The important part being that it splits like this, and we say that operations coming from the Lth component of this splitting are weight L. So weight refers to which arity of the little disks operad it comes from, and being like binary or unary or whatever refers to how many inputs it has. And I'll make one further comment for those of you who maybe know about Steenrod operations, but not these operations. If you allow your chain complexes to have negative gradings and you look at singular chains on a space, or sorry, singular cochains on a space, then the cup product gives that an E infinity algebra structure. And the Dyer-Lashof operations for that E infinity algebra are going to be the Steenrod operations, just different indexing. But so that's the relation to Steenrod operations. Okay. So let me tell you something about what this looks like, or sorry, what the moral of the story is in the classical case anyway. So let's let our field equal FP for a prime P. And Fred Cohen and Peter May showed that that all operations like this are generated by the following operations. So first of all, we have a product, which, as you might guess, is a weight 2 binary operation. So that goes from HK1 tensor, and here I actually do mean tensor, it does factor through the tensor product, tensor HK2 to HK1 plus K2. I also have a bunch of weight P unary operations. So let me call these Q lower I P minus 1. It's a little bit of a strange name, but these go from HK to HPK plus I times P minus 1. And I also have some operations which I'll suggestively call beta QI P minus 1. And these go from HK to the same thing, but in 1 degree lower. And actually these beta QIs, I only need to generate all of the operations when P is odd. So these operations exist for all I between 0 and n minus 1. So in particular, if I'm dealing with an E infinity algebra, I have these for all I. And these are usually called the Dyer-Lashof operations. Lashof. So I'll make one quick comment about indexing. I think the slightly more common way to write these is with a superscript instead of a subscript, and those are just these subscript operations but re-indexed so that they raise degree instead of multiplying by p and doing something weird. So if these feel a bit off to you, that's probably why. I like these because it's really clear, it's a bit more clear where they come from and how they're defined. The other comment to make is that beta qi times p minus 1 is Bochstein of qi p minus 1 if the Bochstein exists. But even in cases where the Bochstein doesn't exist, I still have these operations.
Why does Soren like the upper I and Oscar and Sander? I've never figured this out.
I think it's because of this like raising degree. So it's a bit easier to compose them. Here it's kind of difficult.
But like when you have an E2 algebra mod 2, you only have like one operation in like this lower I notation, right? So it's a lot.
That's correct. Yeah, so that, I mean, that's why I very much prefer this, because it's like all one operation then.
Maybe like, I don't know if some Cartan formulas were, I don't know what's worse.
Yeah,
but.
so that is another thing. So in the same vein as what I was saying of how they compose nicely, I think some of these formulas you have with relations between them are a bit easier to state if you have the upper indexing. So I think that's the main reason. But if you just care about like how they're constructed, I think this notation is a bit more clear. Hopefully that helps. So, okay, so we have these Dyer-Lashof operations, and then the final operation we need, this is just if n is finite, so not for E-infinity algebras. We have an additional weight 2 binary operation. This is a rate as a bracket, and it goes from hk1 tensor, again it actually is tensor, hk2 to hk1 plus k2, and then it raises degree by n minus 1. So this operation is usually called the Browder bracket. So these operations together generate all homology operations, and Cohen and Peter May then used these to compute the homology of the free En algebra on X with FP coefficients in terms of the homology of X with FP coefficients using these. So I won't say more explicitly what that means, but basically the idea is you take a basis for the homology of X with FP coefficients, and you formally formally apply these operations to that basis, and then you mod out by the relations they satisfy, and you show that that's isomorphic to the homology of the free En algebra on X. So that's the sort of free object that answers our initial intuition about that this should be free on that in some way. Okay, are there any more questions about the classical case? I think that's all I'm going to say. Oh, actually, wait, let me give you an example. I wanted to give one quick example of the computations that you can do. So the simplest example to state is if we look at the free E2 algebra on a point. That's equivalent to a disjoint union of unordered configuration spaces of points in the plane. So these are unordered configurations. And their result shows that the homology of the free E2 algebra on a point with mod 2 coefficients, it's a little bit cleaner to state for p equals 2. It's a polynomial algebra with one generator for every power of 2. And this generator labeled by 2 to the I lives in the 2 to the I minus first homology of the unordered configurations of 2 to the I points in the plane. And moreover, this 2 to the ith generator is equal to Q1 of the previous one, the 2 to the I minus first generator. So this is really nice because here you just have this one Dyer-Lashof operation, and you start with this single generator Z1, and you repeatedly apply Q1 to it, and you end up generating the whole homology. So this is the cleanest example, but using their result, you can write down a lot more computations. Okay, so I think now I'll move on to the twisted case unless there are any other questions. Okay, so I've been working on doing basically their story again, but for homology with twisted coefficients. So let me just explicitly write down that goal, which is to define operations on homology with twisted coefficients. And we want to give a description of the homology of a free algebra, a free EN algebra, in terms of these operations. So let me just say a couple of words of motivation for why you might bother doing this. I guess the most obvious motivation is computations. So maybe you have some twisted coefficient system and you want to compute a homology, and having a result like theirs would allow you to simply write down formulas like this. Or maybe you have a spectral sequence where you end up with homology of a free thing with twisted coefficients, and then this could also help with computations there. There are also some more philosophical reasons why this is a reasonable thing to fill in a gap in Fred Cohen's work. It's a bit hard to state those reasons before I've defined some additional machinery that I'll talk about now. So I'm not going to go into detail about that, but if you're curious, you can ask me at the end of the talk.
So like, are you going to try to prove like improve stable ranges for special linear groups? Is that?
So that, yeah, sorry.
Or is that completely not what you're building this for?
So do you have an example of a coefficient system you're interested there?
I was thinking like, isn't the homology of the special linear group basically like homology of GLN with some twisted coefficients?
Oh, probably.
Like, are you going to be able to say like, you know, give some formula or like a conceptual calculation of the homology of the alternating group? Is that like something this machine is supposed to do?
Yeah, so it would be really nice to talk about some examples like that. I would have to think about this.
I can ask you after.
Yeah, sure.
Your talk.
So yeah, I mean, one thing I haven't really done yet is work out specific examples. So I'm going to say right now, like what types of coefficient systems I'm going to consider, and I would have to think about whether those examples fall into this category. But ideally, examples like that would be covered. I just haven't specifically thought about those. Yeah, so maybe we can talk about it a little later. So when we start thinking about which coefficient systems we want to consider, we shouldn't expect to get a reasonable theory if we just consider any old coefficient system. So we need to restrict our attention to some particularly nice coefficient systems, and the ones that I've chosen to consider, perhaps I'll do something more general later, but I'll just be motivated by spaces for now. If I have a free EN algebra in spaces, then I'm going to consider only systems that, so first of all, what I mean by a coefficient system is a functor from the fundamental groupoid of X to abelian groups. And I require that these coefficient systems be valued in a field. So again, we have a fixed field F. This is reasonable because in the classical case, we also worked with field coefficients. And the second thing I require is that these be pulled back from the group completion of X. So if you recall that whenever you have an EN algebra, there's a map of EN algebras to an n-fold loop space. And that's a group completion map. So if I have a coefficient system on Y, a functor from the fundamental groupoid of Y to abelian groups, I can pull it back along this group completion map to obtain a coefficient system on X. And it's much nicer if I work with group complete spaces. So I require that all of my coefficient systems are pulled back like this. And
Sorry,
it turned.
Quick question.
Yes.
X is just the topological space now, or is this already the free EN algebra on something else?
No, yeah, X is just any old space here. And then we want to consider,
and you would, okay.
Sorry, X is an EN algebra in spaces. So it's not necessarily free.
I see. Oh, okay. Thank you.
But yes, in particular, we will care about free EN algebras. And so then if I look at the free EN algebra on X, then its group completion is loops and suspension N. So such coefficient systems, it turns out they're more or less covered by the classical case. If you do a bit of extra work with Fred Cohen and Peter May's computations, if you are working with n greater than 2. So for the rest of this talk, I'm going to just deal with E2 algebras. It seems like this is where there's the most to be done. Okay, so that was sort of which coefficient systems I want to consider. And now I'll move on to the setup, the framework I've actually chosen to work in, which might feel a bit disconnected at first, but I'll try to relate it back to spaces in a second. So I'm going to let C be a braided monoidal category. And given such a C, I want to consider the category of functors from C to chain complexes in F. And I can equip this functor category with a monoidal structure called the Day convolution monoidal structure. And I don't have time to define that, but it's not so important exactly what it is. If you don't know what it is, don't worry about it. The important thing to keep in mind, so sorry, I'll denote this by a circled asterisk. So the important thing that you should keep in mind here is that if your source category is braided monoidal and your target category is symmetric monoidal, then the Day convolution gives a braided monoidal structure on the functor category. So we're working in a braided monoidal category here. And let me tie it back to the space example that I mentioned before. So our motivating example here is where C is the fundamental groupoid of a space Y, where Y is again an E2 algebra in spaces, and it's group-like. So it's already group complete. So another way of saying that is that its pi 0 is a group under the group structure, under the E2 structure. And I'll just remark that if you have an E2 algebra structure on Y, that gives a braided monoidal structure on this fundamental groupoid. So this actually does make sense. And now we can define twisted chains on X. If X is as over here on the left, and we have some coefficient system, so again, where X to Y is a group completion, so Y is group completion of X, we can define twisted chains on X as some object in this functor category from the fundamental groupoid to chains on F. I won't say explicitly how, but it's not so hard to do this. And so twisted chains on X actually make sense as an object in this category. And so this is a reasonable category to work in if we want to define operations. And actually, it solves a lot of problems. If you try to just work in spaces and write things down naively, you have a lot of base point issues when you work with twisted coefficients. And so working in this category will solve a lot of base point issues. So now we'd like to be a bit more general and allow a general category C, but we want to be a little bit restrictive because this is our motivating example. So note that the fundamental groupoid of Y is actually a rigid category. So what that means is that more or less every object has a dual. So here, because every object has additive inverses, we get duals. So we're actually, instead of just considering every braided monoidal category, we're going to look at rigid braided monoidal groupoids as our source category.
Sorry, and what do you mean by dual?
There should be dualizing maps, so they should have like a left and right dual, like X, and you should have dualizing maps from like X dual tensor X to the identity, to the unit, or that sort of thing, satisfying some appropriate equations. And if you have additive inverses, as we do when pi 0 is abelian, then, which it is here, then these satisfy duals.
So should I think like the basic example is like the groupoid is like a z's worth of z's? Is that?
Yes. Yes.
Okay.
Perfect. Yeah, so I'm actually about to simplify things down to just like thinking in terms of abelian groups. So that was a good comment. So there's some work of Joyal and Street that gives a really nice categorization of rigid braided monoidal groupoids. So they do a lot more work than I'm going to talk about here, but we're going to consider tuples A, B, H, C, where here A and B are abelian groups. H is a map of sets from A cubed to B, and C is a map of sets from A squared to B. So again, they're just functions, they're not necessarily group homomorphisms. And they're satisfying some equations that I won't write out because it's not particularly enlightening. But now, given one of these, given some ABHC, we can obtain a rigid braided monoidal groupoid. And maybe I'll write that on the next page so we can keep it up for as long as possible. So I'll denote this by C of ABHC. So this category is defined as follows. The objects are the elements of A. The morphisms, let me say, the hom from A1 to A2 is empty if A1 is not equal to A2. And if A1 is equal to A2, it's just the elements of B. And here, composition is given by addition in B. Okay, and we can also define a monoidal structure here. So the tensor product on objects is given by addition in A, and it's given by addition in B on morphisms. And now I also need to tell you what the associators are. So the associators come from H. So an associator should be a map from X tensor Y tensor Z to X tensor Y tensor Z. And remember, because A is a group, these two objects are literally equal. So a morphism should be an element of B. And this element of B is H of X, Y, Z. And I also need to specify the braidings, the braiding maps. So I need maps going from X tensor Y to Y tensor X. Again, these are literally the same element because A is abelian. So I need to specify an element of B to get a map, and that element of B is C of XY. Okay, so that's all the data. And of course, these need to make some diagrams commute. And it turns out the equations that they need to satisfy to make this a braided monoidal structure are exactly the equations in this definition over here. So we do actually have a rigid braided monoidal groupoid, and it's rigid because, again, A has additive inverses. So Joyal and Street, well, they prove a more general result than this, but the important thing for our purposes is that every rigid braided monoidal groupoid is braided equivalent to one of these. So this is basically taking a skeleton of a rigid braided monoidal groupoid and writing out combinatorially what the structure satisfies. This is a really nice, clean way to characterize the structure. And so instead of dealing with a general category C, we're going to consider the category of functors. I'll call this category D, so I don't have to keep writing it out. Functors from one of these C of A, B, H, C things to chains on F. And so the example here that we had before of the fundamental groupoid, if C was the fundamental groupoid of some group like Y, then the A we get is going to be pi 0 of Y, and the B is pi 1 of Y. And because Y is a double loop space, those are actually abelian, and so that makes sense. And so the universal example that was mentioned before, if we take the free E2 algebra on a point and group complete it, then we'll get that A is the integers and B is the integers. So that's sort of like the universal example, and you have to do a bit more work to figure out what H and C are. Okay, so this gives this like really nice combinatorial way to deal with things. So let me just give you an example of how you can write out the structure much more nicely. So if I have two functors, F and G and D, now I can write out the day convolution very simply. So F day convolved with G evaluated on some A in this object group A. Now it has the formula of the direct sum over A1 plus A2 equal to A of F of A1 tensor over B with G of A2. So this is really nice and simple. And I can also give really nice simple descriptions of the associators and the braiding in terms of H and C. So this just sort of really simplifies the structure. Okay. Oops, sorry, I didn't mean to flip that one. So this category D is the category we're going to be working in now. And so we wanted to define operations on E2 algebras. So I need to tell you what an E2 algebra in this category is. So this is a braided monoidal category. So we need to talk about a braided version of E2 algebra. So maybe most people are probably a bit more familiar with symmetric operads. So a braided operad has a very similar definition, but you basically just replace all the symmetric groups with braid groups. So on the nth arity, I have an action of the nth braid group, and my composition maps need to be compatible with the braid group actions. There are a couple of subtleties, but that's more or less it. So now I need to tell you what braided E2 means. So Fedorowicz defined a braided operad structure on a version of the E2 operad. So he took universal covers of the spaces of the little two disks operad and defined the braided operad structure on that. So these are universal covers of the little two disks operad. So here there are definitely base point issues, but he showed that you can pick any base points you like and still make sense of this operad structure. So a braided E2 algebra should in some sense be an algebra over this operad. So in particular in our category, what that means is if I have some X and D, then an E2 structure on X should consist of having a bunch of maps that go from chains on the universal cover of the little two disks operad, tensored, and here by this tensor product, I mean level-wise tensor. So we're tensoring with a functor. We're doing this level-wise. Tensored over the braid group with X day convolved with itself K times, and this should map to X. And these should satisfy the usual equations. So here, the braid group acts on this, that's part of the operad structure, and the braid group acts on the right, just via the braiding. This is what happens when you swap two copies of X. And this is why in a braided monoidal category, you have to talk about braided E2 algebras, because otherwise you don't have a symmetric group action when you swap things. Okay, so now I can actually tell you what kinds of coefficient systems we want to consider. So remember, we wanted them to be valued in fields. So these are determined by, yeah.
But I think of this as like kind of like E infinity, in the sense that, like, you know, the universal cover is contractible, and also like if you were in symmetric monoidal case, you'd take sort of a universal cover of, well, I don't know, maybe not, but or like this is as commutative as you can be in a braided monoidal case, and then it gives you.
Yeah, exactly. If you sort of go up to E3, then you're already symmetric monoidal. And then I'm not actually sure what your comment is, but.
Oh yeah, maybe whatever. I just say what you were going to say. I don't know if my comment matters. Okay.
No worries. But yeah, this is sort of why E2 is special. Somehow it seems like the symmetric monoidal case is already covered by the classical examples. But for E2, you can talk about braided things, and then this is a bit different. Yeah, so the coefficient systems I wanted to define come from having a group homomorphism from B. So remember, B was the morphisms in this category. So there's a group homomorphism to the units in F, and my coefficient system I'll denote by F phi, and it's the functor that when evaluated on A, the object A, is 0 if A is not equal to 0, and it's a copy of F in degree 0 if A is equal to 0. So that's what it does on objects and on morphisms. If B is an element of B, which was the endomorphisms of 0, then this acts on this lone copy of F by multiplication by phi of B. Okay, so these are the coefficient systems I want to consider. And now I can tell you what homology with coefficients in the system means. So given some X in our category, our homology is now indexed by one element of A and one natural number. So the AN homology of X with coefficients in F phi is now defined to be, well, I can take X and deconvolve it with F phi to get a functor. And now I can evaluate this functor on A. It's a chain complex, and I take its nth homology. So this is the homology that we want to define our operations on. And I'm not going to write out exactly what you do, because you can basically do exactly what we did in the classical case. So the same procedure as in the classical case.
Sorry, I'm going to ask a question. First of all, are you just focusing only on this kind of coefficient system for the rest of the talk, or is this just an example for right now?
Yeah,
okay.
This is the only one we're going to deal with.
And yeah, maybe you can say a word about why. And then the second question was, is why can I take convolution between X and F phi? Is X also a coefficient system? In which category
yeah, so
do each
X,
of these live?
They're both elements. They're both elements of this functor category. So this is kind of the nice thing about working in this functor category. So a coefficient system normally would be like a functor from the fundamental groupoid into, say, abelian groups, which we can then include into chain complexes. So coefficient systems and like E2 algebra sort of live side by side in this category. So they're both objects of the same category.
So, like, if I wanted to get, like, ordered configuration spaces with, you know, in R2 with coefficients in like the sign rep, or, you know, like where if there's if one point goes around another point, or sorry, if 2 points swap places, you get a minus sign.
Yeah.
So would X evaluated on something give you ordered configuration spaces or unordered? If at the end of the day I wanted unordered with these alternating coefficients?
I think unordered.
Oh, okay.
I would have to think about it a little bit, but I mean, usually the way if you wanted to like start with the space and go to this functor category, like if I have some group completion map from X to Y, then I take like chains on the homotopy fiber of F over like the component A. This is like how I get twisted chains in this category. I would, and so if you wanted unordered configurations to be X, then Y would be, sorry?
Oh yeah. So then Y is whatever loops to
yeah,
S2
loops
or something.
to S2. And then this is, I would have to think about exactly what it is, but.
Okay, yeah. But like you could get your phi homomorphism would just be like well,
you're asking here. Yeah, so then I think
there
then your integer should map to -1. Or yeah, like the integer 1 should map to -1 here.
Okay.
I think. Yeah. Yeah, this should definitely be able to deal with that case. I'll actually sort of bring up a slight generalization of that later.
Perfect.
Yeah, I'll give a more general representation on the break groups. So, but first I'll tell you how to construct operations, or rather I won't, because we'll do it the same way we did in the classical case, which I already told you. So operations, going from the product of the AI-Ni homology of X with coefficients in F phi, and landing in the like BM homology of X with coefficients in F phi, will come from the BM homology of the free E2 algebra on a direct sum of, now I'll write something F phi AI-Ni. And so by that, I mean, very similar to in the classical case, it's a copy of F in bi degree AI-Ni, and phi still the morphisms act via phi as before. So the F phi itself would be F phi 0, 0, for example. And as before, this splits as a direct sum using a model for the free E2 algebra of BM homology on chains on the universal cover of the little 2-disk SOP-RAD, et cetera, et cetera. And again, we say that an operation coming from the ELF component has weight L. Okay. So now let me come back to that coefficient system we were talking about a second ago. So this is heavily related to braid group homology. So let me describe now a generalization of the representation we talked about a second ago. So if we have some fixed unit in F, we can, I'll write FQ for F as a module over the kth braid group. And here, the kth braid group acts by the following. So first I map to the integers by abelianizing. And then I map to the units by mapping to an appropriate power of Q. So in the example we mentioned a moment ago, Q should be -1. Okay, so this is an action of the braid group. And it turns out that this particular module will be very important for unary operations. So if I pick a particular Q, which is -1 to the n times phi of C of AA. So remember that phi came from our coefficient system, and C was the function that described the braiding in our source category. Then the BM homology of the free E2 algebra on a copy of F phi in degree AN with coefficients in F phi is isomorphic to, well, first of all, it's 0 if B is not a multiple of A. And if B is a multiple of A, then it's the M minus Kn homology, that number is not so important, of the kth braid group with coefficients in FQ. So in particular, what this proposition says is that unary weight K operations come from this homology of braid groups, of the kth braid group with coefficients in FQ, where Q depends on which degree we're trying to define an operation in. And I'll make a quick comment. I won't write out the proof of this proposition. It's not very enlightening, but basically you just write out this model of the free E2 algebra using this splitting, and you notice that these universal covers are universal covers of classifying spaces for braid groups. So that's where the braid group homology comes in, and you end up with just an F here with a particular action. And because of this nice combinatorial way of describing the braiding in the category, it's really easy to see what the action of the braid group is on that F, and it is precisely this multiplication by this Q. So these braid group homologies describe all of the unary operations, and these were already computed. These were computed in a paper of Ellenberg, Tran, and Westerland. So I already know exactly which operations I get. And in particular, if you look at their computation for a little while, you can convince yourself that the twisted version of the Dyer-Lashof story isn't actually so interesting. It looks very similar to the classical case. So I'm not going to say more about it here. But what I would like to say more about is what happens with the twisted version of the Browder bracket, which was that other operation we had. Are there any questions, by the way? Okay. So this ends up actually being a bit different from in the classical case. So remember that classically the Browder bracket was a weight to binary operation. And so we don't necessarily expect that a weight to binary operation will be defined here. So instead we're going to look for weight M-ary operations, just in case the binary operation isn't defined. And these should go from A1, N1, tensor, AMNM homology. And here I actually do again mean tensor product. The classical Browder bracket factors to the tensor product, so we want this one too as well. And it lands in, well, we sum up all of the A's, we sum up all of the N's, and we add an M-1. Sorry, that's probably getting a bit small for you to see. It's not so important. The main thing is that if the Browder bracket did exist as a binary operation and we iterated it M-1 times to obtain an operation on this many inputs, then that operation would look like this. So that's why I'm looking for operations like this. And candidates for this come from the M-1 homology of the braid group on M strands with a certain coefficient system, which I won't describe because it's induced from one on the pure braid group. So this is isomorphic to the m-1 homology of the pure braid group on m strands with coefficients in F. And I still have a non-trivial action here on F, so let me tell you what that is. So if you'll recall, one way to write down generators for the pure braid group is the following. So I'll call alpha ij the pure braid that takes the jth strand and wraps it around the ith strand, but behind all of the other strands. So here, I is less than j, and they both range between 1 and m. So these guys generate the pure braid group, and then I can describe the action just by saying what each of these does. So alpha ij acts on F by multiplication by a certain unit, qij, which is defined to be phi of c of aiaj squared. Again, phi comes from our coefficient system, c comes from our braiding, and these aiaj guys were the indices that defined our inputs for our operation. Okay, so that's what the action of the pure braid group is on F here. And for untwisted coefficients, we of course already know what this is. So computations of, for instance, Fred Cohen and Arnold, perhaps others, I don't know, imply that if all of the qij's are equal to 1, so that this is trivial coefficient or constant coefficients, then the dimension as an F vector space of this m-1 homology of the pure braid group is m-1 factorial. So that's what happens with constant coefficients. And then we would care, we might be interested in like, how are these operations related to the Browder bracket? So with constant coefficients, the Browder bracket is defined, and you get exactly this many linearly independent operations if you iterate the Browder bracket. So these all come from iterated Browder brackets. So now we'd like to know what happens in the in the twisted case. So I've done some computations to try and figure out what you get here. And some things that I can say are, well, if you look at the product of all of the units, this product is not equal to 1 if and only if the homology is equal to 0. So in this case, you get no operations. If, on the other hand, this product is equal to 1, so we get something non-zero, and we make the further assumption that, sorry, that's an if, and we make the further assumption that no subproduct is equal to 1. So what I mean by that is if we take the product over I less than j and an index set I, where I ranges over all proper subsets of 1 to m, if none of these products is 1, then the dimension as an F vector space of this homology is m-2 factorial. I don't yet have a good reason for why it's m-2 factorial, what that actually means. But the conclusion to draw from this is that in case 2, which I will comment does actually occur. For example, if all of the units are equal to the same unit and it's a root of unity of an appropriate power. So if it's an appropriate root of unity, then this product will be 1 and none of these products will be 1. So that does actually happen. In case 2, we get m-2 factorial linearly independent operations. Sorry, I realize I'm going over 50 minutes. I will wrap up very soon. we get m minus 2 factorial linearly independent operations that do not decompose into operations of lower arity. So here we do not have the usual Browder bracket, but we do have some kind of m-ary version of the Browder bracket. And we know that it doesn't decompose because we made this assumption that no subproduct was equal to 1. And the first part shows us that if the subproduct is not equal to 1, then the lower arity homology is 0. So we couldn't have any operations. So this is actually a bit surprising. And I'll wrap up by saying what I expect the final result to be. This is still a work in progress, so I'll say it as a conjecture. So what I'm trying to show right now is that all operations are generated by the following. First, we have the twisted versions of the Dyer-Lashof operations, which I said before behave very similarly to as in the classical case. We also have these twisted Browder brackets that don't decompose into operations of lower arity. And the final thing we have is a sort of partially defined product. So I didn't really get a chance to talk about the product here. If you wanted to look for where you get operations, an operation that would define a product, you look in the zero homology of the pure braid group on 2 strands with this same coefficient system, and that's 0 unless the relevant unit is 1. So depending on how you look at it, either the product isn't defined everywhere or it's 0 a lot of the time. But I expect that if you take all of these operations, that will generate all operations, and then I can give a description of the homology of a free EN algebra on X as a free object on the homology of X using those operations. So I'll stop there.
Well, thank you, Calista. We tried clapping last time. It didn't really sound too great. So imagine a full room clapping vividly right now for you.
Okay.
Are there any questions for Calista?
I have a question.
Yeah.
So over in the untwisted case over FP, all the operations are generated in weight less than or equal to P, right?
That's right, yeah.
Is something like that true in this twisted case as well, or do you expect it to be true?
No, that's not true because, so in the case, say you just look at pure braid groups, so the free E2 algebra on a point, if you take the coefficient system I defined earlier, where you're just multiplying by a unit, if you take that unit to be like an mth root of unity, where m is greater than P, then I think you should get, you need an m-ary Browder bracket when you have an mth root of unity, and so there m could be anything, I think. So
if you're in characteristic P and something can be a root of unity with more than one order, right? I don't know, but -1 is a second root. This doesn't even have to do with characteristic P. -1 is a second root of unity, and it's also a fourth root of unity, right?
Yeah, sorry. I mean,
does that give you? Okay.
Yeah,
sorry.
primitive nth root of unity. Yeah, sorry. So, yeah.
Okay. I have one other question that's kind of basic, but most of these coefficient systems that you're talking about are not rings, right? Like the one you just mentioned where you're twisting by a root of unity?
Yeah.
So how is it that you get multiplications on the homology with those coefficients?
So actually they should be a ring.
Okay.
Because I can take like F tensor F and take the usual multiplication map to F. And I believe if you make sense of that in the right way, that you do get a multiplication there that should be somehow compatible. So yeah, I sort of philosophically, you should have your coefficient systems need some kind of multiplication, and that should be compatible with the E2 structure in order to get a multiplication on the homology.
The FQ you were talking about, if you tensor FQ with FQ, you get FQ squared, right? Or maybe I'm just tensoring in the wrong category or something.
Yeah, so I was about to ask what do you mean by tensor?
All right.
And then do you mean as a module over which braid group then?
I don't know enough to ask a coherent question here.
Yeah, so I think there the way to make sense of that FQ thing would be to use the F phi notation I've been mentioning.
Yeah.
Where the map here is from Z to the units, and it takes 1 to Q. And so there it's just a copy of F in like by degree 0, 0, and you're multiplying by this Q. So then when you deconvolve with this, you sort of propagate that on all components. So you get this like same coefficient system in every component. And then when you do it that way, then you can tensor them together and you get this multiplication.
Okay. Thanks.
Sure.
Let me ask a quick question. So you said you restricted to these F phi. Is there a particular reason why you did that? Is it one of the reasons for it that it is a ring, like Paul just asked, or
yeah?
Is there interest or scope for more general coefficient systems?
Yeah, so it's exactly what you said, that you first of all need some way to multiply in order, like you need a multiplication on homology basically. So you need to have this coefficient system be like a commutative monoid in this category. So that's why I chose to work with these F phis, because they satisfy that, and they sort of satisfy this intuition I had at the beginning that they're valued in a field. And by defining them this way, they are compatible with the E2 structure. As for working with more general systems, I would like to think about that more. I expect that there are more general systems of interest, and I could probably say something about them. I think if I wanted to consider all systems, that would just be a bit unwieldy, and I couldn't really expect to get a good theory there. But I would hopefully be able to extend this, yes.
Are there any more questions?
So you said like the product is partially defined or often 0 or something. I guess here was like what I was thinking before you said that was I was sort of imagining something like homology of the alternating groups. And then you always have a product, but it's not commutative. It's like commutative up to some automorphism. So I was somehow thinking that that the sort of weirdness in the product would show up in the relations instead of like just the product being 0. But
yeah, so there it depends on which, I guess there it depends on which coefficient system you've chosen.
Or I guess I was thinking maybe, okay, homology, if you're away from 2, the alternating groups are the same thing as the homology of the symmetric groups with coefficients in the sign rep.
Yeah, okay.
So I was thinking homology of symmetric groups, coefficients in the sign rep should always, or at least like you can write down a product like the homology is a ring, but then like with untwisted coefficients, it's graded commutative. But here, I think it wouldn't be, and I was thinking that would be, maybe this is like less general than what you were saying, and like this also shows up, but yeah, I don't know.
Yeah, so I think, I mean, if you'll notice in my description here, I'm not actually finding generators, I'm just calculating the dimension. So ideally, if I had like a more concrete description of this, then I would, if I had like a canonical element that happens to be 0 a lot of times, then I would have like a nice product that's always defined that would just be 0 a lot of the time. So I think what you said is not necessarily at odds with what I said. Like, I think you probably would still get this product. And I haven't really explored much about the commutativity of it.
Oh, and maybe my product actually is 0. Is the homology of the alternating group all 2 torsion in the stable range?
I don't know that off the top of my head.
Okay.
Yeah,
maybe the product I was thinking of like is actually often 0.
Yeah, I think it should just, in many cases that I've thought about, it's just the product just happens to be 0 a lot more than you think it should be.
Yeah, like maybe it like squares to, or like the class of a point like squares to 0, so everything in the stable range is. Yeah. Okay. So maybe it was also. Yeah. So maybe it was just like what you said was true, but like it probably also manifests in like a failure of commutativity.
Yeah.
But that's a different issue, and that's relations that you weren't mentioning.
Yeah.
Another question, and maybe at some point we should invite people to leave the meeting if they want to.
Yeah, maybe Jeremy, maybe you save this question for a second, and I'll ask Zach and Michael if they had any questions, and then we can stop the recording at that point and keep the discussion going as long as we want until it says time. Zach, you had a question?
Yeah, is there a reason you mentioned like top like homology operation? Like, I mean, I thought like Cohen like had something like that when in the classical days.
Yeah, sorry, you were cutting out a little bit. So you're asking about the top operations, is that right?
Yeah.
Yeah.
I think it's like psi maybe.
Yeah, so I kind of hid that in my notation. So you're totally right that there are these sort of top operations that behave a little bit differently. So when I define these QIs, when I is equal to n-1, the operations are a little bit different. And so Cohen distinguishes those and calls them something different, but they're constructed the same way. So the main difference is that for I less than n-1, these operations are actually group homomorphisms, but when I equals n-1, they're not additive, and the error term is given by the Browder bracket. So it depends on how commutative your multiplication is, basically.
Okay, cool. Thanks.
Sure.
Okay, well, thank you again, Calista. I hope you stick around a little bit longer for some more discussion that we can have, but I will conclude the official part now.